Welcome to video 4.5, Geometric Distributions. So in this example, the bottle flip challenge, where you were flipping the bottle and letting it land right side up, took the internet by storm in 2016, and it took classrooms everywhere by storm in 2016. It drove me crazy. So Michael is really good at bottle flipping. On any given bottle flip, he has a 35% probability of landing the bottle right side up. We're going to assume each bottle flip is independent. We're going to define the random variable x as the number of flips it takes until Michael lands a bottle flip. So this is really important, until he lands a bottle flip. So what they're saying here is that we're looking for the probability of first success. And that's a really important note to make, because they're not telling us Michael's going to flip the bottle this many times. What's the probability of something happening? They're saying what's the probability, how many flips is it going to take until he's first successful? This makes this a geometric distribution, the probability of first success. Okay, just like with our binomial distribution, we have some conditions we need to check, then make sure they're met in order to go forward. So we have B, it's the same as for our binomial. It needs to be binary, and so we have land or doesn't land. So we're good there. We've met the binary condition. Independent, it says right there in the problem, assume that they're independent. So that was stated in the problem. So we're fine on our independent. The F, we talked about it as being a T. It's the trials to first success. So you're really looking for first success here. And we've got that. And then your last one is your probability of success has to be the same each time. They said that's 35%, so I'm going to say P equals 0.35. So we've met the conditions for a geometric distribution. So now we can go ahead and look at answering the questions. So first we want to describe the distribution of X, which is the number of flips it takes until Michael lands a bottle. So we're going to talk about the shape. We're going to talk about the center. And we're going to talk about the variability. All right, so our shape is right skewed because a geometric distribution is always right skewed. Now the reason for that is we're talking about the probability of first success. So if we're looking at a long run of flipping bottles, so if we have our space here, we have he's successful on the first one, or he's successful on the second one, or the third one, and this could go on forever and ever and ever and ever and ever, conceivably. But you're going to have a lot more initial successes in the beginning than you do much later. It's very unlikely to flip the bottle 500 times before the first time you're successful. So that's going to make your geometric distribution right skewed. Okay, now define the center. Well, I'm talking about a geometric distribution, and I know on my formula sheet we have a section that talks about geometric distributions. So when I look at my formula sheet, here it is, geometric distributions. The center will be the mean, and there's the formula for it. So I'm just going to take that information and I'm going to plug it in. So to find the mean of my random variable x, it's 1 divided by p, which is 1 divided by 0.35, which when I calculate that out gives me 2.86. Now 2.86 is the expected number of flips to first success. So that's that expected value. Okay, now our variability is standard deviation, so I go back again to my formula sheet, geometric distribution. Here's my standard deviation formula, so I'm just going to take that and I'm going to plug into it. So we'll have the square root of 1 minus p, the square root of 1 minus p divided by p. So we have the square root of 1 minus 0.35 divided by 0.35, which gives us a standard deviation of 2.30. So that describes our shape. Now we want to go on. Find the probability that it takes Michael 4 flips until he lands the bottle right side up. So we're really looking for what is the probability that the first time he lands it up is exactly on the 4th term. So let's think this through without even referencing the formula. If Michael's going to be successful the first time on the 4th trial, so we have 4 trials. That means he missed, and he missed, and he missed, and then he made it. Okay? So that means we had 3 misses. Well, the probability of a miss is 0.65. So I'm going to say 0.65. And he had 3 of them. And then on the 4th trial, he was successful. The probability of being successful is 0.35. So this is the geometric formula from the formula sheet. It's pretty logical. It makes a lot of sense. If we were talking what's the probability he made it on the 10th time, for the very first time, you'd have 9 failures and 1 success. It's always the failures is 1 less than the total number because you're successful on the last one. If you put this in the calculator, calculate it out, you get 0.096. Now this can also be done in your calculator. So we're going to go into our distribution, which is right here at vars, so second vars, and I arrow up because these are at the bottom. We have a geometric PDF and a geometric CDF. We're asking about a particular number, so that's our PDF. So we'll write down geometric PDF. Okay, so let's select that and see what it asks us for. It asks us for our p-value, which is 0.35. That's the probability of success. So I'm going to put my parenthesis, 0.35, and I'm going to label it with p. The exact trial that I'm wondering about is trial number 4. That's my x value. Press enter, and look, we got the same answer, 0.096. Okay, in order to receive credit on the AP exam and FRQ, you have to identify that it's a geometric distribution and define your parameters. So if you're going to use your calculator and you're not going to set up the formula, that is perfectly fine. But you must keep in mind that you must define the parameters and get full credit. So you have to say this is a geometric distribution, which we've done right here. And then we have our parameter of 0.35 and our value of interest. And so this would be acceptable. You'll get credit for that. Okay. All right. What if I don't want to know a particular value? What if I want to know a range of values? So in that case, what you would need to do, so in this one we're saying within the first 4 flips. So what they're really saying is the probability on the first flip, or the probability on the second flip, or the probability of the 3rd flip, or the probability of the 4th flip, which we already know. You would have to calculate all of these and then add them together. It's going to take a while, and there's a lot of chance for mistake because you're trying to rush. So we can go into our calculators and we can use the CDF function. So second vars, you want binomial CDF. Our P is 0.35. Now, the value of interest. Now think about it, within the first 4. So we have all these choices. We have success on the 1st, 2nd, 3rd, 4th, 5th. I mean, we could keep going. Okay? We want within these first 4. So we want to accumulate through 4, and what the calculator will do with CDF is find the individual probabilities and add them up for us. So we're going to calculate through 4. and we get 0.821. So we need to write it's a geometric, and we use CDF because we're accumulating a range of numbers, 0.35, and we're still accumulating to 4. So if we look at this part, they look the same, but the difference is this letter, whether it's the individual number just for 4 or 1 and 2 and 3 and 4. Okay, and we get 0.821 there. All right, well, that was helpful. If you have any questions, let me know, and I'll see you in class.